Okay, so this is Armor's Geometry, Chapter 2, Section 6. Proof statements and segment and angles, or proof statements about those things. So, last section we talked a little bit about proofs and the beginning of proofs. This section sort of gives it a formal definition. And it says proof is a logical statement that shows that a statement is true. There's tons and tons of ways to show a proof, paragraph proof, etc., etc. You can even write like fill in the blank proofs. But the main proof that people do, and when we talk about proofs, the main type of proofs that we talk about is a two-column proof. And a two-column proof is a proof where there's just two columns. And one column is called the statements or statement. And the other column is called reasoning or reason. A lot of the cases I'm just going to call it R and S to save time. S, R. And this section is your statement, whatever you observe or see. And this side is your reasoning, why, the proof, the theorems, the postulates, the rules, the definitions, all the sides that is the reason why these things are happening. I'm going to go through each example of these proofs, and then we'll move on. This one here was already done in the previous section, so it won't take too much time to go over it. But we have a scenario where angle 1 is equal to angle 3. So CBE is equal to DBA, or A, because 1 is equal to 3. Then we say what it forgets to say, and what I said last time is EBD is equal to itself. So actually let me do this. So angle 1 is equal to angle 3. Notice it put the number of the step, so it'd be like step 1, angle 1 is equal to 3. Why? Because it's given to us in the problem. Our first one is always going to be given. And step 2, we can say that angle EBA, I'm just going to write EBA to save space, is equal to angle 1 plus angle 2. Then we can write for step number 3 that DBC, or no, they substituted. Since I know 1 is equal to 3, I can say that EBA is equal to angle, oh, I did this wrong, angle 2 plus angle 3. Then I can say that EBA is equal to angle 2 plus angle 1, because I'm substituting 3 in for 1. So this reasoning is the segment angle addition postulate. So I'm going to write A, P, angle addition postulate, and then substitution, the substitution property of equality. Number 4 says, okay, angle 1 plus angle 2, I can write it angle 2 to be consistent. Angle 2 plus angle 1 is equal to DBC. Select EBA is equal to 2 plus 1, and 2 plus 1 is equal to DBC. A equals B, and B equals C. And there we get that A equals C. So for step 5, we have EBA is equal to DBC. This is also the angle addition postulate. And EBA is equal to DBC because of transitive property of equality, which says that if one thing is equal to the other and that same thing is equal to something else, then those two guys must be equal to each other. Another proof that they give, or sort of they're asking, is they want you to give the reasonings for this situation. And what do they give us? They give us A, B, and C. They tell me that it's given that AC is equal to AB plus BC. Oh, AC is equal to AB plus AB. AC is equal to AB plus AB. Nice. They want me to prove that AB is equal to BC. So they give us this guy. Here's my statement. Here's my reasoning. The first thing that we always start off with is our givens, and in this case it's AC is equal to AB plus AB. Why? Because that's given to us and that's written down there. The second step they give us is that AB plus BC is equal to AC. AB plus BC is equal to AC, and that's because of the segment addition postulate. Next step they give us is AB plus AB is equal to AB plus BC. Alright, so here's what happened. If you look at our initial AB plus AB equals AB plus BC, you look at our initial, you basically can see that from here to here we substituted. We have AB plus BC equals AC here for the segment addition postulate. Then if you look at our given, we have AC equals AB plus BC. We have AC over here, we have AC over here. We can substitute these guys for each other. So we're going to use the substitution property of equality because we're subbing on the right hand side here where it's AC. We're subbing AB plus BC for AC over here. So that's substitution. Then the last thing we're going to do, notice there's there AB on both sides. So I can subtract AB on both sides and I get that AB is equal to BC. And that's because of the subtraction property of equality. which says that I can subtract the same thing from both sides and equals our main true. Yeah, so that's that one. They talk about what a theorem is. Yay, theorems. And theorems is a statement that can be proven. It's a statement that can be proven. Now, we've talked a lot about postulates and properties. Those are basically rules that don't have to be proven. A theorem, on the other hand, does have to be proven. And they give us Theorem 2.1. This is our first of many, many, many theorems. And Theorem 2.1 is basically talking about congruent segments. And the first of it is the reflexive. So we already know what reflexive, transitive, and symmetric are. So we know them for equality. This is about, actually let me change this. We'll use the simple congruent segments. We don't know about the symmetric property of equality. And we know about the transitive property of equality. Now, instead of TPE, this is TPC, transitive property of congruency. So reflexive property just says that a segment is congruent to itself. Symmetric property says, let's make this red. Symmetric property says if AB is congruent to BC and BC is congruent to I'm tripping. If AB is congruent to CD, then CD is congruent to AB. We can flip the order. Transitive property of congruency, TPC. If AB is congruent to CD and CD is congruent to EF, then AB is congruent to EF. Transitive property of congruency. That's Theorem 2.1 for segments. Those same three things apply in 2.2. Theorem 2.2 and Theorem 2.2 deals with congruent angles. These are the same rules, but instead of segments, we're dealing with angles. So reflexive property, angle A is congruent to angle A. Symmetric, if angle A is congruent to angle B, then angle B is congruent to angle A. Transitive property, if angle A is congruent to angle B, and angle B is congruent to angle C, then angle A is congruent to angle C. Okay. The same three rules. But one is for angles, one is for segments, and these are all congruency, not equality. These are congruency. And these are theorems, so these things can all actually be proven. They want to name the property shown. So CD congruent to CD, that is reflexive. Angle Q is congruent to angle V. Then angle V is congruent to angle Q. That is symmetric. Okay. Alright. This is actually a really good one. You will see it again in life. We have this segment here. Oh man. That's a little better. A and B. They give me that M is the midpoint. And it's the midpoint of AB. And they want me to prove that AM is equal to 1/2 of AB. Alright, here's my statement. Here's my reasoning. The first thing they give for proof for number one is always going to be your givens. M is the midpoint. I don't have to write of segment AB. You can if you want to. And it's given to me. So, since M is the midpoint, I know that AM, segment AM, is congruent to segment MB. And they're congruent because of definition of midpoint. And if you're thinking, well, where did you get that definition of midpoint? It's a definition that we got back in chapter 1. So all those definitions I asked you to write down in postulates, they're going to come back to bite you in the booty if you didn't write those down, because those postulates and rules and definitions are going to stick with us for the rest of the course. So hopefully you wrote those down. If not, you might want to write them down right now. Definition of midpoint. Notice that in the proof, they want us to prove, they want to put us to two things. They want us to prove that AM is half of AB. They also wanted to prove that AB is equal to 2 times AM. That equality sign is different from the congruency sign. So we have to change this from congruency to equality. And this is what the third step is. If something is congruent, then they are equal. Notice that the segment symbol goes away on the little line on top when you deal with equality, but we have the segment symbol when you have congruency. So AM is equal to MB, and this is definition of, I write congruency, definition of congruency. I actually just do def and then the congruent symbol. The book is more formal, definition of congruent segments, but you can write definition of congruency like that, which says that if something is congruent, then they're equal. And we're going to use this definition a lot to change from congruency to equality and equality to congruency. When you are adding stuff or subtracting stuff, we have to use the equal sign because it's talking about a specific value. When we talk about length, we use congruency. So since we're talking about something that's being added and equal to something, we have to change it from congruency to equality. We can now say using the segment addition postulate that AM plus MB is equal to AB. Segment addition postulate. Then we can say, what are we trying to prove? Okay, AM. Then we can say that AM plus AM is equal to AB. What did we do? We got back here from line 3 that AM is equal to MB, so we substituted AM for MB. So we use the substitution property of equality, but we'll just call it substitution. And then here, this is our 6th step, but this is rule number 8. That's the first thing they wanted us to prove. And that's going to say that 2AM is equal to AB. Now, the book says the distributive property, which is correct. It is the distributive property. You can also say simplify. I'm okay with either one. For those who need a refresher on their distributive property, AM plus AM is equal to, I can pull out the AM, and I can say this is equal to AM times 1 plus 1, right? There's a 1 in front of this A, there's a 1 in front of this AM. So I can pull out the AM, I can factor out the AM, put the 1 plus 1 in parentheses, then that turns into AM times 2, and then I can just put the 2 in front, which is 2AM. So that's where that comes from, using the distributive property. Or you could just add the 2 AMs using combining like terms, and that gives you 2 AM. I will take either one. And then the last step, step B, this is 7. We're dividing 2 from both sides, so we can say that AM is equal to 1/2 AB, which is the last thing they want us to prove up here, and that's because of the division property of equality. Division property of equality. Okay. They ask a question here. They ask a what if. What if instead of looking for AM, I'm looking for MB? So what if this changes? I don't want to prove that AM is equal to 1/2 AB. I want to prove that MB is equal to 1/2 AB, and etc. and etc. What do I do? Well, these rules are exactly the same. The only thing that changes is this part right here. Instead of saying AM plus AM equals AB, I now have MB plus MB equals AB, because I'm trying to solve for MB. So then anything with AM in it turns into MB, and this turns into MB as well. So essentially I'm substituting the other half. Since they're equal to each other, I can substitute either one for the other. So in this case, I'm now just subbing MB for AM, and I can solve for MB as well, using the same steps, using the same properties and theorems. Any theorems in here? Same properties and postulates. Alright, so concept summary for writing a proof. 2-column proof. Statements are on your left. Reasoning is on your right. You can number the steps. Most proofs try to be efficient. So they try to get to the conclusion in the least amount of steps most of the time. But the number of steps can be very long or it can be very short, depending on how well you are confident in various properties and theorems and postulates. And they can be a little tricky at first. Try to sort of think of a strategy to get there. So here is the proof of the symmetric property of congruence. We said that this was a theorem, right? So what they do in this proof is that they have two angles, angle 1 and angle 2, and they're told we're given that angle 1 is congruent to angle 2. So we have to prove that angle 2 is congruent to angle 1. Here's the thing about this. We can't use the symmetric property of congruence to prove the symmetric property of congruence. So we have to prove it without using the symmetric property of congruence. So this is a proof of symmetric, I'm going to shorthand it, property of congruence. And like I said, you can't use that to solve a theorem. You can't use the theorem to solve the theorem. Hence, it wouldn't make sense because we're using it. You can't use something that you're trying to prove. So first step is always our given. Angle 1 is congruent to angle 2. That's given to us. Then we can say angle, they use the measure. The measure of angle 1 is equal to the measure of angle 2. So you put the measure part if you're talking about equality. So this is definition of congruency, or definition of congruent angles. I'm just going to write definition of congruency. I'm never going to write angles or segments, just for the sake of time. If something is congruent, then something is equal. Okay, now that we have that squared away, we can say that the measure of angle 1, or 2 rather, is equal to the measure of angle 2. This is the symmetric property of equality. So you're like, well, I know what you're thinking. Well, wait, I thought you said you couldn't use symmetric property to prove symmetric property. This symmetric property is a symmetric property of equality. I can use the symmetric property of equality to talk about the symmetric property of congruency. They're not the same thing. One is congruent, one is equality. And while it's the same type of rule, I can switch the order. Whoopsie, this should be angle 1. I can switch the order. It does, since it's talking about switching the order of equality, doesn't really mean switching the order of congruency. It's sort of like a loophole. It's neat. And if something is equal, then something is congruent. So this is the definition of congruency. So two angles are congruent. If two angles are congruent, then two angles are equal. If two angles are equal, I can switch the order given the symmetric property of equality. And again, if two angles are equal, then two angles are congruent. Therefore, 2 is congruent to 1. Neat. Okay. So this particular property is a pretty good one. So let me explain it. We have a scenario. We have A, B, C, D, not to scale. And we're told that we have a segment here, B, is the midpoint of AC. And if B is the midpoint, then I know that AB is congruent to BC. We're also told that C is the midpoint of BC. So this guy is congruent to this guy. Notice that there's overlap. And because we have this overlap, we're going to use that to solve our problem, or set up our proof, or finish our proof. So what are we given? We're given that B is the midpoint of AC, and we're given that C is midpoint of BD. And then we got to prove, write this, prove that AB is equal to CD. Okay. First step is our givens. B is midpoint. I'm not going to rewrite the whole thing because I already wrote it up there. C is midpoint, and that's given to us. Step number 2, I can say that since B is the midpoint of AC, I can say that AB, segment AB, is congruent to segment BC, and that's because of definition of midpoint, and that's from chapter 1. Again, all those definitions we went over are on all fair game and on the table for proofs. And then we can also say that BC, segment BC, is congruent to segment CD, and we can see that in the picture. AB in the red ticks. AB is congruent to BC, definition of midpoint, and BC is also congruent to CD. Again, definition of midpoint. Okay, well, if AB is congruent to BC and BC is congruent to CD, then we can say that AB is congruent to CD. And we can say that AB is congruent to CD because of the transitive property. In this case, it's of congruency, TPC. Transitive property of congruency, because we're dealing with congruent segments. If something is congruent, then something is equal. So then we can say that AB is equal to CD, and that's definition of congruency. It would say congruent segments, but I'm just going to call it definition of congruency. All right, 5-step proof. Since we were given that we had the midpoint, the same segment is congruent to different sides, so we can use a transitive property to say that those two things are congruent to each other, and then we turned it from congruency to equality by using the definition of congruency, or congruent segments. Okay. They have some sort of thought questions here. So number 4 is question 5 says, does it matter what the actual distances are in order to prove the relationship? And the answer is no, because since we're dealing with congruency, we could turn congruency into equality, so we don't have to actually have an actual number to explain that they're equal to each other. And we use the proof to show that that's not the case. We do not need numbers. 6, they say there's a clothing store. So if I was to rewrite this thing, they say there's some type of store in the middle. So you have A, B, C, D. Actually, make it a little bigger. A, B, C, D. And it says, hey, we have some other thing in here. A clothing store in the middle. We can call it E. And it's in the midpoint. So I can say that that guy is congruent to that guy. We've already established that these guys are congruent to each other. So they want to know, well, what's the other two stores that this thing is equal to? So we know it's equal to BC. We know that BE and EC are the same. They're equal to each other. So if I was to substitute BE for BE and add them to both sides, so those guys know that they're equal, I can say that this distance from A to E is congruent to E to C, E to D, just based off the drawing. So A is the food court and D is the bookstore. So the clothing store is also equidistant to the bookstore here, and it's equidistant to the food court. So that's all they wanted you to know from that. They didn't want you to prove anything. Okay, that's our section, our introduction into proofs. Hope you have a great rest of your day.